Right, so let us talk about the next problem, which is problem 550. So in this case, we have an acrylic sheet which has a thickness of 5 millimeters, and this is used to coat a hot isothermal metal substrate. Okay, so we are coating it on a hot surface, and the substrate temperature is given to us, that is 300 degree centigrade. The properties of this acrylic sheet are given to us. We have the density, the specific heat, and the heat transfer coefficient, the thermal conductivity. So neglecting the thermal contact resistance between the acrylic and the metal substrate, so there is no contact resistance as such, we have to determine how long it will take for the insulated backside of the sheet, okay, so it's insulated, to reach its softening temperature. Okay. So the acrylic sheet becomes soft at 90 degrees centigrade. So we have to find out at what how long does it take for this. So on one side we have 300 degrees centigrade, and on the other side we want to figure out how long does it take for that to reach 90 degrees centigrade, and the initial temperature is 20 degrees. So the whole sheet acrylic sheet is at a temperature of 20 degrees centigrade to start with. So we'll call the T initial as 20 degrees centigrade, and since this we have the metal substrate here, and there is no contact resistance on this side. Okay, so what that means is, if there's no contact resistance between two solids, then that means that this temperature is the same temperature as the metal temperature, which is 300 degrees centigrade. So we'll call it TH. So TH is given as 300 degree centigrade. And now this side is insulated, so that means there is no heat loss from this side, and we have to figure out how long does it take for this temperature to reach the softening temperature, where T softening is 90 degree centigrade. Okay, so we have studied these kind of problems in transient heat conduction. So if you remember that when we have an insulated boundary condition, this is the same as having this thing as 2L, okay, and this has exactly the same boundary condition as the right hand side, and that is what we did. So we used one of the boundary conditions as the insulated boundary condition because of the symmetry condition at the center. Okay. So if you remember, the case that we studied was this one, and then we had convection on both sides, but in this case there is no convection. In fact, what we are saying is that there is the temperature of the surface is known. Now that is still all right, because if there is no convection, then what we can say is that the resistance of convection is 0. So we can use the same results we obtained for the convection case, but assuming that the convection resistance is 0, or 1 by H is equal to 0. So that is, this implies that our H tends to infinity. And in fact, since we non-dimensionalize the boundary conditions, so we use the bio number as in the boundary conditions. So in fact, one of the boundary conditions was del theta star upon del x star at x star equals 1, which was this boundary was equal to minus bio number times the theta star value at this boundary. Okay, so since our bio number is HL by K, so if my H tends to infinity, my bio number tends to infinity. So what I can do is I can use the same results as earlier with this bio number tending to infinity. So if I quickly, I mean, I don't need to solve the problem again. I can simply use the solution. So the solution, I will write that for you. Let's write it here. well, let's do it here. So the solution we have was theta star. Theta star was given as t minus t infinity upon ti minus t infinity, and this was given as a summation of an infinite series with a coefficient. I mean, it's a cosine term with the amplitude which was varying as minus xi square Fourier number. Then we had a cosine term. I mean, we had an exponentially decaying amplitude for the cosine term. Okay, so the cosine term varied with x star, and then we had an amplitude varying with t star or Fourier number. Okay, and in this case, the xi-n's were solution to the transcendental equation, which was given as xi-n tan xi-n was the Biot number. So in this case, we are solving this equation for Biot number equal to infinity. So we can go and look in the tables and find the solution for this equation for xi-n when my Biot number is tending to infinity. Okay, so that's available in the tables, so we can do that. So basically the idea is that we can use the same solution we obtained for the convective boundary conditions, but in this case substitute Biot number tending to a very large value, and the tables provide the solution to this equation for Biot number tending to infinity. And once you have these in values, you can substitute them in the series. I'm sorry, the Cn values are also given in terms of xi-n. Okay, so Cn is a function of xi-n, so that is also given to us. So we can use that, substitute everything in this equation, and obtain our theta star value. In this case, it is the other way around because we have T is given to us. So T is the temperature at. I mean, we are actually solving it for a given value of x star, which is for x star equals 0, because this point is x star equals 0. So that simplifies the situation. So this becomes cos 0, which is 1. So we simply have a summation of Cn e to the power of minus xi-n square Fourier number. Okay, so this term is actually 1 because x star is 0. Okay, so this xi-n can be obtained from this. Well, you have multiple xi-n values because this equation has multiple roots. Okay, so as I said that this T is in this case the center line temperature, which is given as 90 degrees. T initial is 20 degrees, and T infinity in this case is 300 degrees. Okay, so you substitute those values and you get the value of your Fourier number, and Fourier number is nothing but the non-dimensional time. So Fourier number is alpha t by L squared. So you can, since alpha and L both are known from the data that's given in the problem, so we can calculate the time value at which the center line temperature here becomes it becomes 90 degrees centigrade. All right. The other thing we can do is, because we have lots of terms in this series, so it may become difficult to solve this. So what we can do is we can approximate this series as only the first term, because we can see from this exponential decay term that the amplitudes decay exponentially. So the contribution of the subsequent terms is much smaller than the previous ones. So we can assume that the solution is only, I mean, the first term in the series dominates the overall solution, and we can approximate that for theta star. Then you can calculate the Fourier number, and if the Fourier number is greater than 0.2, only then we can safely approximate with the first term. So we can check that condition as well.